Good day, my name is Lolandra Dennis, and today we shall be discussing the development of an electrical power takeoff system for a sea test scale offshore wave energy device. So, based on the name of the system, it is implied that the system's main aim is to provide monitored electrical power through wave energy. Let's discuss the system's design and specific arrangement. The Ocean Energy Buoy is a floating bent backward duct buoy type 1-5 wave energy converter such that the actions of waves forces water to rise and fall in a chamber called an oscillating water column. The moving mass of water displaces the air above it in the chamber. This bidirectional oscillating airflow is directed through a duct to a Wells turbine which produces rotational mechanical power. The principal requirement of the power takeoff system is to provide a means of converting pneumatic energy from the action of the oscillating water column into electrical energy and to dissipate this energy safely. The system should provide a means of sensing ocean conditions as a basis of starting the turbine, motorizing the turbine to a defined operating speed, allowing the turbine to capture pneumatic energy and converting this to electrical energy. This setup should also provide a controlled mechanical load to the turbine to maintain a fixed speed operation in so far as ocean conditions allow, dissipate the generated electrical energy, supervise the deceleration and shut down the turbine when sea conditions subside. The system is also to detect errors or operation out of design range and take action to protect the system, log all pertinent data to allow analysis of the device and power takeoff operation, while operating and supervising the system remotely via telecommunications. The monitored power takeoff is comprised of turbine and turbine duct, electrical machine, power electronics, electrical power source, and electrical load. The energy required to run the turbine up to operating speed must be supplied from an electrical power source that's on board and stored or displayed on board as well. The Wells turbine converts aerial power to mechanical power within a limited range of airflows. This produces one-directional mechanical torque in the presence of two-directional airflow and is not self-starting, also exhibiting strong aerodynamic stall at air velocity to tip velocity ratios exceeding a critical value. The system is to have robustness, maintainability, usability, environmental suitability, and safety. Now that we've discussed the system's design, let's focus on its operation. The operation of the power electric system can be divided mainly into motoring and generating. For the motoring aspect, the requirement is to provide a control torque from an electric machine to accelerate the motor, shaft, and turbine from standstill to a defined operating speed. In the generating aspect, the objective is to apply a control torque which opposes the pneumatically generated turbine torque, maintaining constant shaft speed. The power electronics converter is required to provide a means of controlling the machine current for suitable load resistance. A buck converter provides the required range of control. In addition, identical devices are chosen for both motoring and generating aspects, although currents are significantly higher in generating mode. A large number of sensors set up are to provide control loop inputs and condition monitoring data, with sensor signals being variously conditioned and scaled by circuitry on a custom-designed printed circuit board. It also became necessary to use a reflective laser sensor mounted in the turbine duct, providing a short pulse each time a reflective element on the turbine nose cone passes a fixed sensor element to sense turbine rotation. This sensor, despite limitations, proved the sole source of accurate speed information available without a significant refit of the turbine. This power takeoff system's ability to maintain a set speed is limited by the lack of grid connection, so, in the absence of input wave power, the system will decelerate. Lastly, but with underlined importance, today, let's discuss the testing of the system. The system's testing in the laboratory was facilitated by the construction of a test rig. This test rig, which mimics the complete onboard power takeoff, comprised of a DC machine, a flywheel, and a mains inverter-fed induction machine. The DC machine has similar electrical characteristics to that on the device. The flywheel mimics the inertia of the turbine, and the induction machine is controllable to emulate wave energy inputs. The induction machine was supplied with electrical power from the diesel generator on the support vessel. A variable speed drive was utilized to allow control of the generating speed or torque. For commissioning tests, the mechanical power was controlled to mimic the action of waves on the device and turbine. It's noted that there were no failure events in the power takeoff system, and sustained and successful operation was achieved. As a result of the careful and robust design philosophy, a recommendation is that connection to the mains electrical grid onshore at a suitable voltage level should be considered for offshore wave energy test sites, even those of reduced scale. Thank you for taking the time to listen to my video presentation.